force on each wheel. Okay, so it would just be, and they said that the mass of the whole car, wheels included, is M, right?
Mm-hmm. Yeah.
And so we know that all that mass is being held up by 4 contact points. So that means that each of those contact points must be holding up 1/4 of the total mass. So that means each of these 4 wheels would have a normal force pushing up on it, and that normal force would have to be equal to 1/4 of the total mass times gravity. Did they say we're allowed to use G in our answer?
Yeah.
Mm-hmm.
Yeah, MMG.
Yeah, so I think it's just 1/4 mg.
Tricky.
Because yeah, it's tempting to do, because they told us that the mass of the tires is like what? NW?
Mm-hmm.
So it would be tempting to say NW times G, because that's like, oh, it would just be the mass of the tire times gravity. But we have to take into account that the tires are not only holding their own mass, but it's also holding the mass of the rest of the car. Part D. Now assume that the frictional force F is not at its maximal value. What is the relation between the torque applied to each wheel by the axles and the acceleration of the car? Once you have the exact expression for the acceleration, make the approximation that the wheels are much lighter than the car as a whole. Express your answer in terms of some or all the variables M, R, T, and G. So it wants to know the acceleration of the car. We've got torques acting like that. So it should just be, I think they're trying to make it sound more complicated than it is, but if we just think about this equation, sum of forces equals mass times acceleration. We already know what our net force is, it's 4F. And we know that the mass of our whole system is M. And we're looking for A, so it should just be 4F divided by M. But
What is it talking about when it says the moment of inertia is I equals Km
yeah,
R squared? Is that?
it's relevant later. It doesn't seem like this question's really asking for it.
Yeah.
But yeah, moment of inertia just means how much an object resists being rotated.
Okay.
So like we know, for example, mass, if we go back to like the beginning of the semester when we thought about things linearly, we could have 2 objects, one that has a lot of mass and one that has very little mass. And if we want to get both of them going the same acceleration, the big mass is going to take a lot more force to get it accelerating the same way as the little mass. So it's the same thing with rotational stuff. Some things are easy to rotate, some things are difficult to rotate. And so I and mass are very similar. If something has a lot of mass, then you know it's hard to get it going or it's hard to make it stop. If something has a big I value, that means it's hard to get it rotating or hard to stop it rotating. So the frictional force is not at its maximum value. Oh, so I guess that's why we can't use this simplified way, maybe. So the frictional force is not at its maximum value. What is the relation between the torque applied to each wheel by the axles and the acceleration of the car? So